about my two books. I may write a third one if I ever get around to it. The first book, which I talked about last time, covers the creation of the universe to the fate of the universe. And in between, within that book, I discuss things like the way stars work. Because in order for the universe to reach a point where it could generate life and planets, the original hydrogen and helium generated during the Big Bang needed to be placed through stellar furnaces and smashed together in nuclear fusion to make heavier elements, of which we're all a part. Carl Sagan's famous, we're made of star stuff. So that's what the first book is about, and it talks about the fate and scale and size and whatnot of the universe. The second book, it was originally one book, and it got to be too big in many different ways. So I've split it into two books. The second book now covers many other topics that I've talked about over the years in Science Sunday. And in fact, Science Sunday was the inspiration for me writing these books and for giving these talks. And as long as I live and have the memory, I will say that I'm extremely grateful to Mike Winter, who's over here being my artistic assistant, for inviting me to participate regularly in Science Sunday. So it has enriched my life. I hope that science enriches your lives too. The opinion that I maintain, and which I expressed last time, is that science is the way to know what's real and true and possible in the world. And since I've always been a person afflicted with an undying curiosity, learning about science has been part of my intellectual journey all my life. And so being able to share that in Science Sunday has been enriching to me. I hope it's enriching to you. And these books are a direct consequence of some of the presentations I've given. So this second book deals with what I call modern physics. Philosophers of science and some physicists will quibble a bit about the inclusion of one of the early topics in this book, and that is Einstein's theory of relativity. According to some scholars, relativity theory is the last what is called classical theory of physics. So it's right up there with Maxwell's equations and Maxwell's theory, and it's an inheritor of Galileo and Newton's work. Galileo, in fact, had his own version of relativity. He noticed that when you drop a cannonball from a moving ship, that the cannonball falls straight down, even though the ship is moving. You might think that since the ship is moving, you drop the cannonball, and the cannonball goes like this, because it's just going straight down from where it started. But it actually falls relative to the ship in a straight line down from the height from which it was dropped. So that Galilean relativity helped inspire some of the thinking that Einstein did. So this talks about relativity, and then it gets into more widely accepted terms for modern science. So quantum mechanics, particle physics, and ends with symmetry theory. Symmetry theory is a notion of the way different interactions in physics. So you may know interactions by the more common term of forces. For the weak nuclear force specifically, it's a little bit of a misnomer to call it a force. It's more appropriate to call it an interaction. And there are four known basic interactions that allow material and energy within our universe to interact with each other. The gravitational force you're familiar with, and the electromagnetic force. Magnetism and electricity are related to each other very intimately, and I'll talk a little bit about that in a few more minutes. And then you've got the nuclear forces, the strong nuclear force, which gives us nuclear power and nuclear weapons, and the weak nuclear force, which allows some particles to transition from one sort to another sort. So it's responsible for things like beta decay, where an electron can shoot out of a nucleus of an atom. Well, there aren't any electrons hidden previously in that nucleus. Instead, some of the particles in the nucleus transition into new sorts of particles, one of which is the electron. So that's what this book is about, and the symmetry theory comes into play because the best way, the best model, and I talk about this in the first book, the idea that everything we understand about nature and the world and each other and any place or activity we're engaged in results from a model we maintain in our minds. A model about the way the world works, a model about the way navigation works, the model about how our spouses behave, a model about, you name it, right? We have all these complicated models in our mind about how the universe works. And one of the things that science tries to do is it tries to codify these models more formally, and it tests them to make sure that they're not just opinions. Well, I think my spouse is, a jerk or whatever. I don't. My spouse is in the back. Is a wonderful person, yes. That's right. So, but it would be hard to formalize that, right? That kind of model. So physics specifically deals with model that can be formalized with mathematics. Mathematics is a kind of language, and that's how I open this book. The second book opens with a discussion about mathematics, and why do we use mathematics in the context of understanding reality. So here's a representation of some mathematical, a plot of some mathematical functions you might be familiar with. One of them is linear growth. That would be the red line. All right, you can recognize a line. That's linear growth over time or distance or whatever your coordinate axes are. And then the blue line is one you don't encounter very often. It's cubic growth, something that increases like x to the third power. You're probably at least familiar from your primary school education, the idea of a parabola, which is like x squared. All right, well, you can also graph x cubed and x to the fourth and x to the 99th and whatnot, right? So those are simple graphs of powers of x. And then finally, you've got what's known as an exponential curve shown in green. I'm sure you've heard about exponential growth, right? Exponential growth when a population is provided arbitrarily large amounts of food and space, a population of bacteria will grow exponentially. A population of lemmings will grow exponentially. A population of human beings will grow exponentially. This is one of the ways biology manifests itself, is exponential reproduction. But there are other things that follow exponential curves. I talked about nuclear power. When you bring too much of a radioactive isotope together, it can have an exponential curve kind of response to ever increasing amounts of nuclear matter. You don't need all the nuclear radiation emitting matter in the universe brought together to make an arbitrarily large nuclear explosion, right? You add just a little bit more and just a little bit more, and you're on this exponential curve, and you can get a nuclear explosion. Or you can dampen that growth and control it and get nuclear power. So there are many things in the real world that follow an exponential curve. One of them that you may have heard about if you've dealt with technology at all or read stories about technology is something called Moore's Law. Have you all heard of Moore's Law? All right, Moore's Law, I think it originally said every 18 months the power of computing gizmo, right? A CPU, microcircuits, whatnot. The power, the computing power, the processing power, the number of calculations per second, et cetera, those double every 18 months. That's Moore's Law. Well, if you double something over time, think about starting with 2. This is easy for those of us who deal with computers. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, et cetera, right? We've essentially memorized these. But that's what a doubling looks like. And look how fast, over like 8 generations, it got really large, to a really large number. That's exponential growth, right? So Moore's law is essentially an exponential heuristic. Now, it's not a law backed by physics. It doesn't say this will happen because the universe is built in such a way that it must happen. It's sort of a heuristic for understanding kind of what it's looked like over time. Well, if you've been following technology for the past 8 or 10 years, you may have read that Moore's law has slowed down. Maybe it's every 24 months, or maybe instead of computing transistors getting smaller and smaller every 18 months, maybe instead computer scientists have started investing in multiple CPUs in a single package. Even your mobile phone, if you have a smartphone, your mobile phone has a CPU in it that has multiple computing centers in one little device. It used to be back in the 90s when you bought a computer with a single CPU. And then there were dual core CPUs, and there were quad core CPUs, et cetera, et cetera. So one of the ways they've gotten around some of the limits to growth that might have emerged in CPUs is they've started stacking CPUs together. But even then, with those kinds of innovations, the growth seems to be slowing down. So this heuristic notion that technology is on an exponential curve may not be borne out in fact. And there are other kinds of exponential growth that people have worried about. Thomas Malthus, back in the 1700s, wasn't that right? He was in the 1700s, wrote about what happens when there are 100 billion people in the world, and using an exponential growth trend, I don't know that it was 100 billion, but he came up with this calculation, says this is what's going to happen. The world is going to run out of horses to provide us with locomotion. It's going to run out of turnips and other kinds of food stuff that that a farmer can grow in a farm field. This exponential growth is going to run us into trouble. And then in the 70s, there was a book, Limits to Growth, which also talked about exponential growth and the perils of it. And then Ray Kurzweil, back to technology a little bit. Some of you may have heard of the inventor and futurist Ray Kurzweil. Ray Kurzweil talks about an event he has deemed the singularity, when computers become sentient. And he bases that largely on an extrapolation of an exponential curve. So exponential curves are all around us, and we integrate this notion into our thinking. Things just keep growing and growing and growing. The energy use in the world. I gave a talk about this. This was probably the first or second Science Sunday I ever did, was about the amount of energy use in the world. And one of the conclusions from that is, in something like 200 years, if the rate of energy use on planet Earth continues to increase, well, every time you use energy, you produce a little bit of waste heat. Your engine in your car or your electric motor in your car produces waste heat. Your vacuum cleaner produces waste heat. Your dishwasher produces waste heat, et cetera, et cetera. Everything that uses energy must necessarily eventually radiate that energy away as waste heat. Well, if you follow that out by a couple of hundred years and you trace the exponential curve tracing out the growth of energy use on planet Earth, the amount of waste heat generated would exceed the temperature of the sun. Right?
So
Now,
these are basically models that people are using exponentially, because at some point, from some point here to some point there, and even by the nature of exponential growth, it starts out at a small, unnoticeable amount. So up until some point,
Right.
the exponential growth seems valid. It fits in with, this model fits in with what we perceive.
right.
But the potential for it to continue is where the model can fall apart.
Right, and that's going to be my next slide, so you're on top of this. So there are economists who may be accused of ignoring some of the natural limits to growth that the universe imposes upon us, like the fact that the Earth, if it even approaches the 5,000 degree temperature of the surface of the sun, will become slightly inhospitable. right? And, right, yeah, things might be self-correcting before that, right? So you can't just always naively assume that exponential growth is going to happen. And in fact, nature, as Mike has so presciently determined, nature typically follows a curve that looks like this. And if there's any, if there's like 50 concepts you take away from Science Sunday, I hope this is one of them. And this is a curve called the logistic curve. It's got a different French root than the logistics that you hear about with like shipping packages and stuff. It's same spelling, but it's a different meaning in mathematics for what's known as a logistic curve. You can think of logarithms as closer to the root of this one, right? And if you're early on in this curve, close to the far left side, it can look a lot like an exponential growth curve. But something always intervenes to stop it, right? If it's a population of bacteria that's growing, they run out of food, they run out of space. If it's the amount of energy used on Earth, something stops it, either the amount of available energy, right? We don't create energy, we liberate it from different things, whether it's the moving air in the atmosphere or the nuclear force and interaction locked up in nucleus, or the chemical energy of fossil fuels, or the energy directly coming to us from sunlight. We extract energy. We don't create energy. And there's a finite amount of energy we can possibly extract from any given source. So exponential growth in 200 years that causes us to heat up like the sun is not going to happen, not because of any inherent limitation to human survivability in high temperature environments, but because there just isn't that much energy available, right? So there's a
term in biology called carrying capacity.
Right, carrying capacity, that's great.
Right. So a certain plot of land can only sustain so many deer or whatever, and they overbrowse if there's more deer. If it's such a nice sustainable area or nice supplying area, they'll grow and grow and grow, potentially at an exponential rate, until they hit this carrying capacity, and then they'll die off.
Right.
And things will start again. Other things will feed on their carcasses, and they'll start exponentially growing.
Mike, you're jumping ahead a slide again. I love that about you. And here it is, right? So what happens if you transition from, let's say that you lived 300 years ago where the only way to get around on land was a horse, or your own legs, or maybe the legs of a camel, you know, whatever, some kind of load-bearing animal. Well, if you think about the logistic curve of that, there is the fastest speed that a horse can carry you over a given amount of distance, right? Over a short distance, it's pretty fast. Over a longer distance, like a trip to your long-lost relative that lives 8 miles away, you know, then a horse can't move all that fast. So you can think about the logistics curve of the speed of a horse. Oh yeah, wow, this horse, I can just make it go faster and faster. Oh gosh, well, I guess this horse can't go any faster. Yeah, the Pony Express, thank you, right. Or you can come along with steam engines. Steam engines. We even had steam engines racing horses at one point, and the steam engines eventually won. So steam engines, you can make them go faster and faster and faster, and eventually they blow up. And you can't make them go any faster. You can't build them any larger. They reach a limit. So if you stack the speed of horses, you put that on the bottom, and then you put the speed of steam engines on top of that, and then the speed of electric motors and gasoline motors, and the speed of rocket ships, and the speed of the Voyager probe, and on and on and on. Well, can you always go on and on and on? Right? Is there a speed limit? Yeah, it's the speed of light. Nothing can, no mass can ever accelerate to a speed equal to or greater than the speed of light. The universe says, nope, can't go faster than that, no matter what. I don't care how big your rocket is, I don't care what kind of fancy propulsion system you use, you can't go faster than that. And in fact, one of the things I write about in the first book is you really can't safely go even 10 or 20% the speed of light, because our galaxy, although empty enough that you can see for thousands of light years, you can see distant stars because space is largely empty, it's not completely empty. It's got little bits of dust and little stray atoms and whatnot, and if you're going at something like 20% the speed of light, that stray dust and those wafting atoms become deadly projectiles that can rip apart nearly any spaceship you could conceive of. So there are limits even to how fast we can go, right? We haven't done a whole lot more than jet planes in terms of terrestrial speeds. We've got some hypersonic devices, but then you get into limits of human tolerance for acceleration and other things like that. So you can think of many natural processes that seem to be exponential as stacking these curves. Well, that's the same thing that happened with technology. I talked about the microprocessors, right? The first generation of microprocessors was making a single computing core go faster and faster and faster. And then that kind of ran into some limits, so they started saying, well, let's put another, and let's put 10, and let's put 64, and let's put 128 cores together. And then let's put 5,000 computing units in your graphics card. Your graphics card is a supercomputer if you've got a modern graphics card. Okay, so those concepts about the relationship between even the simple notion of exponential growth and the natural world can illuminate a lot of interesting physics along the way, like the speed of light being a limitation, or the amount of energy available to us being a limitation, right? And that illuminates, hopefully, one small aspect of the chapter I wrote about the relationship between mathematics and science. This is just one example. All right, speaking of the relationship between mathematics and science, one of the other things I have in here, as I alluded to, is a chapter about relativity. And relativity is a special, there's a special theory of relativity and the general theory. Special doesn't mean that it's his favorite. It doesn't mean that it needs more attention than other theories. It means that it's a special case of a more general theory. And in fact, the general theory is called the general theory of relativity. So this is a special case of relativity. And it's still mind-blowing enough that professional physicists have problems thinking about some of its consequences in extreme environments. But here's one of the simplest equations to come out of the special theory of relativity. It's a little more complicated than E equals mc squared, which, by the way, I talk about in the book, and I show you how it's derived from the philosophical notions of relativity, why E equals mc squared, and what it means. But this is a slightly more complicated formula out of the theory of special relativity. You may not be familiar with it, but it only involves fractions and square roots and things raised to the second power. So it's pretty easy in terms of the mathematics involved. But a lot of people, myself included, I can't look at an equation like this and intuitively understand its behavior, right? I'd have to think about it. You'll notice that the only thing really operational about this equation is the little bit that says v squared over c squared. V squared is your velocity in some reference, relative to some certain reference frame, and c squared is the speed of light. So actually v squared is your speed, and c squared is the speed of light. They're not vectors, they don't have a direction. That's important, but kind of an aside. So this just says something happens. This gamma factor, whatever the heck that is, changes. That's not a y way over there to the left of the equal sign. That's a Greek gamma. That's a conventional term. Something happens as your speed approaches the speed of light. And I don't know, without really thinking about it, I can't just imagine with my little pea brain what happens here. But what we can do is we can plot it out. So here's a plot of what happens to that gamma factor as we approach the speed of light. Over on the far right of that little graph, the little blue line, it just zooms up toward infinity. This is even faster than an exponential curve. So it starts off modest and it stays modest until about 80% or so of the speed of light, and then it just shoots up, right? Well, this factor, this gamma factor in the theory of special relativity relates to things like how does a moving clock compare to a clock that you presume is stationary? How does a moving mass, or more specifically, how does the momentum of a moving object change with its velocity? Momentum, you probably learned in high school, momentum is mass times velocity. Well, that's not true in special relativity. You have to take this gamma factor. Momentum is mass times gamma, right? And in the simplest low speed, low compared to the speed of light case, that simplifies to mass times velocity. But the better, more accurate representation is it's mass times gamma times velocity. But the important part is the fact that momentum increases tremendously because of this effect of special relativity. And this is not intuitive. And then here's another plot. Let's say we have something that changes like 1 over gamma. So this is the relative speed of a ticking clock that you might measure in a spaceship that zooms past you. You're watching a clock tick, 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 as it flies off into the distance. As that spaceship approaches the speed of light and you watch the interval of those ticks compared to the interval on your stopwatch or your heartbeat, you'll see that those ticks, as it becomes closer to the speed of light, it goes tick, 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 right? And that's what this curve describes, right? The interval, the comparison of the intervals of different watches. And that's all because of this same gamma factor. It's whether you multiply by gamma or divide by gamma. And notice that this traces out a half circle. Isn't that interesting? Circles are interesting in geometry. Circles are simple. If you've got a circle somewhere that comes out of physics, of a physics equation naturally, it's telling you something deep about the way the universe works, right? And this points to what's called a symmetry. I mentioned symmetries a minute ago. I talk about this more in the book, right? I've only got an hour now, and the book would take me more than an hour to read to you. But that circular trace of one version of this equation that comes out of thinking about the fact that the speed of light is a speed limit in our universe. That's where it comes from. If you think about that carefully, like Einstein did, you come up with this sort of circular trace. And if you've got a circle, that's a special kind of symmetry, right? A circle looks the same no matter how you turn it, unlike a square, which looks a little different if you've got it at different angles. A square is only symmetrical if you flip it by 90 degrees at a time, right? You understand that? But a circle has what's called a continuous symmetry. And there was this brilliant mathematician who lived about the same time as Einstein. Her name was Emmy Noether. And Emmy Noether figured out that any time there's a continuous or circular, you can think of, a continuous symmetry exhibited by a mathematical rule of nature, a law of nature that is specified by a symmetric kind of equation, it means that there's a conserved quantity. And this is the part that will blow your mind. I don't have time to get into it in detail today, but you could read about it in the book, and that is the conserved quantity that must arise because of what's called a Lorentz. This is a Lorentz equation. Lorentz is a guy who preceded Einstein, who was looking at some of the effects of the Michelson-Morley experiment. Again, a lot of background. And he came up with a mathematical explanation for why that experiment gave the results it did. And he came up with this equation, but he didn't really understand what it meant or why it's true. And Einstein figured all that out. In any case, it's called a Lorentz, that circle is called a manifestation of Lorentz symmetry. So according to the ingenious Emmy Noether, who Einstein looked up to, by the way, according to Emmy Noether, there must be some conserved quantity in nature arising from the fact that this symmetry exists. This is a symmetry only due to the fact that we have a speed limit, the speed of light in our universe. And you know what that conserved quantity turned out to be? This is going to it blew my mind. No. Electric charge. The fact that electric charge is conserved in our universe arises because we have a fixed speed of light. Isn't that amazing? Right? And I go into some detail about that in the book. Yeah. Yeah, why don't we wait for the microphone?
I was just wondering, is that a chicken and the egg type situation, or is it truly that one causes the other, that, I forget already which way you said it goes, but
Yeah.
whether charge came first, so to speak?
Right, that's a good
or
question.
Or the speed of light came first?
Yeah, so when you're looking at an equation, things on the right-hand side and things on the left-hand side of the equation, you don't necessarily say which one came first. You just say that one thing is related to the other, right? There's a mutualism that happens there, right? And so it's not that one phenomena preceded the other and made the other necessary. It's that any time, Emmy Noether discovered that any time you have a continuous symmetry in a mathematical representation of a law of nature, anytime that happens, there will be always an associated conserved quantity. Symmetry in space, you can move from here to there, momentum, symmetry and momentum anywhere in space. I can do an experiment measuring momentum here or on the moon or in the Andromeda galaxy, et cetera, et cetera. Emmy Noether's theorem says that because motion and momentum are conserved, actually, I got that backwards. Because I can conduct an experiment at any given place, I can do it here, there, Andromeda galaxy, because of that symmetry of being able to do an experiment anywhere in our three-dimensional space, momentum is conserved. She also said that because we can do an experiment yesterday, today, tomorrow, a trillion years from now, because there's a symmetry in time, energy is conserved. So the conservation of energy, the conservation of momentum, the conservation of charge, some of these things you might have heard about anecdotally throughout your lives, these arise because of deep symmetries in the laws of nature. This is amazing. And so symmetry theory, which I talk about in the last chapter of this book, looks for symmetries in mathematical laws of nature associated with other conserved quantities, right? They kind of go backwards from what you're saying. Instead of saying, oh, we've got this law of nature and it's symmetric, there should be a conserved quantity, it says, oh, look, we've got this conserved quantity, like electric charge or whatever. We may discover the conserved quantity first, but that leads to a description of a symmetry theory that describes the interactions associated with that phenomena. It's beautiful. This is the most beautiful extrapolation of modern physics.
I'm just wondering, Scott, you're blowing my mind here, but I'm thinking on this conserved charge, are there 4 kinds of charge that makes them all add up to a constant unit? You know, you have 4 quadrants. If it's conserved,
The circle.
There's got to be a plus minus, but 4 quadrants. In my mind, you're saying there's got to be 4 kinds of charge. You know, the sum total of the whole thing is 1 unit. That's just how my mind is. But you're blowing my mind here. So
Okay, that's a brilliant question. So what our friend has done is he's recognized, I think, that that plot of a circle was only a 1/4 of the circle, right? So if you extend that, it's got 3 more quarters of a circle to go. Does that mean there are 3 additional kinds of charge? The answer is no, and the reason for that answer is because I kind of chose a way to represent this symmetry in a way that's most intuitively accessible, but you can represent it as a complete continuous symmetry, a sort of rotation in Lorentz space. And once you analyze that symmetry, you discover that there's only a conserved quantity, and that conserved quantity is charge. And charge can take on a positive or negative value, just like momentum can take on positive or negative value. But energy, because time only has the forward direction in our universe, among other reasons. Energy only has a positive value. So lots of deep insights can be obtained from this. So I wanted, last time I spent quite a bit of my time reading from the book, and I thought that displayed too much of the top of my thinning hair. So I'm not reading as much this time. But what I will do is read a little bit, and I wanted to read about electricity and magnetism. So this is a little section from the book. In prior sections, should you have read them, you might have noticed a conspicuous absence. After setting the context for Einstein's special theory of relativity and belaboring how it was derived from a deep contemplation of the implications of Maxwell's equations for the way light behaved, I did not talk about electromagnetism. I only talked about clocks and rulers and nothing about electromagnetism. Is there any way electromagnetism relates to relativity theory? I will answer that question and perhaps another of your curiosities presently. You know now that particle accelerators and racing airplanes cause relative time differences, but you might wonder if there's ever been proof of a length contraction. That's one of the consequences of relativity theory that I didn't belabor right now. Certainly nobody has ever been able to measure a speeding jet airplane to determine if it shrinks relative to a stationary airplane. Even so, there's an everyday situation which would simply not exist without the reality of relativistic length contraction. The Lorentz transformation predict discrepancies among various measurable quantities as seen by different observers in constant relative motion. They have a lot to teach us regarding surprising time, length, and mass energy changes arising from relative motion between observers. Yet there's nothing obvious in these relationships about magnetism and electricity. Are these phenomena immune to relativistic effects? Does an observer moving past an electric charge with its associated electric field have complete liberty to assume that he or she is at rest and it's the charge that's moving? Even more interestingly, does the strength of some or other property of an electric field change if it's in relative motion, analogously to the way clock intervals and rulers change? Or is it a constant like the speed of light? One of the most well-established facts of electromagnetic physics is moving charges create magnetic fields. This canonical example is the magnetic field associated with a current-carrying wire. So here's a current-carrying wire with some charged particles in it. In a conductive wire, the tiny, almost massless electrons are so loosely bound to their atoms that they can move around in the bulk of the wire material. This electron freedom is a property that makes these metals metal-like in terms of their ductility, conductivity, and propensity to reflect light. Whenever metal carries a current, electrons have an overall bulk movement aligned with the electric voltage difference. Some people, this is not what I wrote in the book, but an interesting aside, some people think that electrons move through a wire nearly at the speed of light or at the speed of light. And that's not true. Any given electron moves incredibly slowly, only a fraction of a millimeter per second. About 0.0002 meters per second is the average speed of an electron in a copper wire carrying a current. But there are billions of them, so the overall effect is bulk movement of charge and an effect of the electric field. This movement of charge is what powers electronics and other things moving charges do. Give rise to magnetic fields. Another thing moving charges do is to give rise to magnetic fields. This warrants some scrutiny. The electrons in a conductor, say a wire, moving against a background of essentially fixed atoms. So the lattice of copper atoms is fairly fixed. The electrons are moving a little. Move against a background of fixed wire, which having donated some electrons to the sea of electrons floating in the wire, thusly have a net positive charge. The spacing between these atoms is fairly constant as well, and we can think of them as comprising a kind of charge lattice throughout the wire. while the electrons ooze and flow within this lattice. Now imagine a charged particle, perhaps an electron, moving along parallel to, but outside of the wire. That's the little blue dot I've drawn with the gold arrow underneath it there in the diagram. It's moving parallel to, but outside the wire in the direction of the net electron flow inside the wire. The wire itself, even though it carries current, has a net neutral charge. This is because the negative electrons jostling and flowing freely have their charges exactly and perfectly balanced by the stationary cores of metal atoms containing their positively charged protons. As our imagined electron moves along outside the wire, the Lorentz contraction discussed earlier becomes important, even though it's only moving at a fraction of a millimeter per second. If this Lorentz effect gives rise to a bunching up along the direction of motion of the atoms within the lattice of fixed atomic cores in the wire. This bunching up is more pronounced for the stationary atoms in the wire, and less pronounced for any of the distances between electrons flowing or moving within it. The bunching up of positively charged atoms relative to an electron moving alongside the wire means that our imagined electron moving outside the wire sees a net increase in the density of positive charges compared to the density of negative charges. This difference in charge densities experienced by the moving electron arises only and precisely because of the relativistic Lorentz contraction effect. I'm not going to read the rest of this, but that essentially says that an electron outside of that wire, because of the moving charges and the very slight, but billions of times over billions of electrons summed together, or cumulative effect of the current flowing, an electron outside the wire sees slightly higher density in the protons that are stationary in the wire compared to the electrons that are moving in the wire. And what does that do? The electron, which has a negative charge, is attracted to the protons in the wire, or the leftover positive charges in the wire. And so the electron moves towards the wire. There's another way to describe this if you take college-level electromagnetism in your first or second year of college physics. The other way to describe this is that the electron experiences a magnetic field which deviates it and bends it towards the wire. But the magnetism in this case is just an illusion. It's what we see based upon the context of the situation. The electron only responds to the electric charges in the wire, the bunching up of the protons due to the Lorentz contraction. So that's relativity at work in a conductive wire. The fact that conductive wires have magnetic fields arises because of relativity, and it helps to explain the relationship between electromagnetism and Lorentz invariance that I talked about a moment ago. And I go into a little more detail in the book about that. All right. This is an equation that some of you might be familiar with in a slightly different form, but this talks about an interval between 2 points in space. The distance, the ds squared, is equal to the distance, the separation distance in the x-axis squared plus the separation in the y-axis squared plus the separation in the z-axis squared. That's standard Euclidean geometry, Pythagorean theorem kind of thing, right? You've all seen something like this in your education. What relativity theory does is it comes along and Einstein tacks on another term. He says that space and time are somewhat interchangeable. So you've got this time factor here. So now, instead of adding up all these factors for distance, you then also subtract, and that's important. It's led many graduate students astray in ways that I'm not going to talk about right now. But if you could just change that negative sign to a positive sign, you could solve an equation for the universe. Really can. It's awesome. But nature doesn't allow you to do that. You have to do the minus sign. And because we have that minus sign, it means there's always a trade-off between distances measured in space and an interval measured in time. that there's always that trade-off. And Einstein actually called his theory of relativity, his preference would have been to call it the theory of constants, the theory of invariance. That was his preferred term for his theory, was the theory of invariance, not the theory of relativity. Because he was saying that any two observers, no matter what their relative motion, will always agree about this quantity. They will always agree about what's called the interval separation in space-time. And if you've got a space-time that's relatively flat, you can still have amazing effects like Lorentz contraction and electric currents and whatnot. But what happens if you take this Euclidean geometry and you allow it to bend and warp? And this is the last thing I wanted to talk about today. So imagine, if you can, I have some learning aids for you. So what I just handed to you is a piece of empty grid paper with a grid drawn on it, right? This is flat space-time. This is the space-time of special relativity. Now, if you take that paper and you twist it or warp it or bend it a little bit, but I want you to look at it flat on and notice how, don't notice the curvature in three-dimensional space. This is kind of tough. I want you only to pay attention to the way the grids look different. The grids no longer look like little square grids. They look warped, right? Right, they look like trapezoids, right? So this is a model often used for the theory of general relativity. You take some flat sheet, like a rubber sheet, and you draw a grid on it, and then you put a bowling ball in the middle of the rubber sheet, and it deforms the grid, right? And if it's a grid that's drawn correctly, then you've got, you can see, literally see the warping of the coordinates, the x and y coordinates that make up that grid. But there's something really, really misleading about that analogy. You know, your phone light is on. I don't know, back in the back. You might be running your battery down. There's something really misleading about that analogy. It leads people to ask a question like, well, if space-time is bent, what does it bend into? Right? You see an image of a black hole represented on a rubber sheet, bending the sheet. Where does the sheet bend into? Does it bend into the third dimension? If four-dimensional space-time is warped, does it warp into a fifth dimension? This is a perfectly natural and really excellent question. And the answer might surprise you. And I'm going to show you a way to figure out that answer with Silly Putty. If I can get the Silly Putty out of the container. Yeah, they come in these nice, convenient eggs. They're usually about this big, but all right. So I have over here, can I have them? Yeah, there's a microphone here. Yeah. First, I need to flatten my Silly Putty. Physics is hard work. Yeah, you're right. All right. I thought this would be fun. I write about this in my book. In fact, this is the newest section I added just this week because I had a conversation with Joanne. And Joanne often helps me clarify my thinking, and if not my thinking, she makes me realize I need to do a better job of explaining something. So I came up with this Silly Putty thing. I haven't seen this used in any other book, so if you want a unique treatment of general relativity, buy my book. And Silly Putty. All right. So, you know, that idea about the warped rubber sheet, that highlights something that mathematicians and physicists recognize as a distinction between what's called intrinsic curvature and extrinsic curvature. Extrinsic curvature is the bending of the rubber sheet into three dimensions. In order to explain and appreciate extrinsic curvature, you need to add dimensions, right? The rubber sheet has to bend into something. So what happens with intrinsic curvature, which you've probably never heard of before. It's written about in graduate texts for relativity, but you don't typically see it written about in regular books about Einstein's theory. If you pick one up at your local bookstore, they're not likely to talk about the distinction between intrinsic and extrinsic curvature. But I'm going to do it. And I think it's a concept that is insightful and illuminating, and anybody can understand it if all you have in your mind is an image of silly putty, or if you have in your hand some actual silly putty. So here we go. This is a nice big flat piece. So Mike, could you hold that up? So this is our grid paper, and Mike has helpfully drawn with a nice greasy pencil. You know what silly putty does, right? Drawn with a nice greasy pencil these lines indicating the grid of space-time. This is flat space, all right? What does general relativity do? Mike, can you lay this down here so I can press this silly putty on it? Hopefully. Hopefully you can see the grid on the silly putty. I apologize for the fact that the silly putty is bending a little. That's not part of my intended demonstration. I want it to be flat, all right? So this is a flat piece of silly putty, regardless of what you see. And it's got a space-time grid on it, demarcating maybe the x dimension and the time dimension. We can pick two, because it's two-dimensional. Now, instead of bending it, what I'm going to do is I'm going to do this. Now, look at my nice flat space-time grid. It's not extended, work with me here, it's not extended into 3 dimensions. It's still just a 2-dimensional grid. But you see the warping? That is intrinsic curvature. You can figure out intrinsic curvature when you're embedded in the space that you're measuring. You don't have to appeal to or go into another dimension. This is the way general relativity works. It describes the compression. I can also do this. I can really squish this in here. All right? And imagine what I've done to those lines now. Again, ignore the 3rd dimension. Right? So I've squished this grid. You can squish it, you can contract it, you can expand it, you can bend it this way, but not this way, right? That's intrinsic curvature, and that is the curvature described by the mathematics of general relativity. It uses something called the Ricci, R-I-C-C-I, the Ricci tensor. Ricci tensor was developed by a mathematician back in the 1800s, and Einstein appropriated this mathematics to describe what's called a non-Euclidean geometry. It's not a flat geometry. It's a geometry where there's inherent warping. But it's intrinsic. You don't have to think about the 3rd dimension. If you extend this to the idea of a gelatinous cube or a silly putty cube that has a grid drawn all throughout it, you can think about warping that cube, right? Well, there's a kind of mathematics that deals with this called tensors. They're an object that's kind of a extrapolation beyond the idea of a vector. You use tensors. Material scientists and structural engineers use these tensors to describe the stresses and strains within a bulk of material, right? They don't have to appeal to a dimension outside the material. They just describe the forces at work inside the material, an intrinsic representation. The mathematics gets a little complicated, but the idea, the basic geometry, is really straightforward. You describe the intrinsic curvature of space-time, and you don't have to bend it into another dimension. Space-time is 3 dimensions of space and 1 dimension of time that have this funky minus sign in here, so they've got this trade-off kind of relationship. And all of that can be explained intrinsically without appealing to what space-time bends into or expands into, etc. There's one final thing related to this I want to talk about. And that is gravity that you experience here on Earth. Most of the gravitational effect that you experience on Earth is not because of a warping in space. If I could start this experiment all over again, or this demonstration all over again, I would stretch this and warp it in only one direction. And that would correspond to the direction of time. If you look at that equation up there, look at the last term, the t squared one. Notice that t squared is multiplied by the speed of light. The speed of light is a conversion factor between measurements in distance and measurements in time. And the speed of light is humongous. So when dealing with general relativity, if you've got a tiny, tiny little compression or extension of the time coordinate, it leads to a huge effect, much bigger than the effect of compression and contraction, etc., in a spatial coordinate. Most, by far, by a factor of the speed of light, big, the effect of gravity you feel sitting here in this room is because of a distortion in the time coordinate due to Earth's gravity rather than the spatial coordinates. To get a distortion in a spatial coordinate, you need a lot of mass, like a whole galaxy's worth, that distorts space enough that you can get a distant galaxy, the image of it, coming to us through space, distorted. It takes a hell of a lot of matter to distort space. It takes a relatively small amount of matter to distort time enough that we feel gravity. And I talk about that in the book too. And that's all I had for today, other than to give you a brief. There are things I didn't talk about today. There's chemistry, a little bit about chemistry. There's a little bit about particle physics, the way atoms look, the way they work, how chemical bonds work a little bit, the basic building blocks, the particles of nature, and then symmetry theory. So there's more. All right? But I'm out of time, and I hope you enjoyed today's talk.
Any fast questions or thoughts that people want to bring up? All right, yeah, it's a lot to take in. The book is available on Amazon.
Yep.
Right? And check it out and bring it in, and Scott will sign it for you, I'm sure. So, 2 weeks from now, you're going to be on a trip.
Yep.
And I'm going to be on a trip, and we'll have Jim Walters, who's talked about evolutionary psychology a couple of months ago, end of
Last year, yeah.
beginning of this year in the spring.
Oh, did he? Yeah.
Yeah, and it's a very interesting topic. It's talking about what sets humanity different from primates and other species out there. What about our evolutionary psychology shows up in our actions and our way of living our lives? So I think there's free posters he says he's going to bring along and share for that too. So probably ask Joanne to handle the second mic for questions and things like that from him as well too. But that's 2 weeks from today.
And pick
right
up a
here.
poster for me, Joanne, if you wouldn't mind.
What's that?
Pick up a poster from him for me.
Yeah.
I'd like one of his
me as
posters.
well, yeah. So feel free. Hope you can make it for that. I think he does a good job. It should be an interesting topic. I think it's kind of his cause celeb.
Yeah.
This is his baby. He loves it. He's a doctor of psychology, I believe.
Right.
And so this is really an interesting topic for him.
Yeah, he knows it well, and he can explain it well, and should be a good talk. So
Yeah.
thank you all for coming. I'm willing to stick around for a few minutes if you have other questions or discussions related to
You gonna
today.
go
Yeah.
out for lunch?
Yeah, we can go out for lunch too.
Yeah.
What's next for the particle accelerators? What are they looking for now?
Yeah, what are they looking for now that they found the Higgs particle? Well, they're looking for things called axions. They're looking for things called supersymmetric particles. Remember I talked about symmetry theory? One of the musings that physicists have done is the notion that if you build an even bigger, higher dimensional kind of symmetry, then it can explain the properties and interactions of the particles that we know about. You need a really higher dimensional model to do that, but when you do that, some other consequences come out of that model, and those consequences are things called supersymmetric particles. They put an S in front of it for supersymmetric, so instead of the electron, you have the selectron, you have the sproton, you have the sneutrino, right? These supersymmetric particles, which are expected to be much more massive than the particles we know about, but so far they haven't found any evidence of them. They keep ruling out new energy domains. Axion is a good candidate for dark matter and a new particle, but they haven't definitively found it. Cosmologists may find that before particle accelerator folks do. And then they're just, smashing watches against a stone to see what flies out. So with higher energy particle accelerators, they're just hoping to see some hint of some new interaction. And there may be a hint of a new interaction. It might prosaically be called a fifth force of nature, but if so, it operates at such a tiny scale and such a huge energy that it has no relevance to even the way stars work. It's so esoteric. It might have been relevant during the Big Bang. So there's a whole bunch of unexplored territory between the energy level we can explore with accelerators and infinity, and they're taking baby steps along that to see if anything new pops out.
This is slightly off your topic, but what are the images from the new telescope tell us?
Oh,
In like a few sentences.
the images from the James Webb Space Telescope in a few sentences are telling us that something's wrong with our theory about the developmental history of the universe post-Big Bang. I'm going to talk more about that in December. So every December for the past few years, I've done a talk I call Cosmic Ornaments. And I usually talk about beautiful discoveries that come out of astronomy for the past year. And I'm going to do that again this December, and I'll be talking about some of the implications and findings of the Hubble telescope during that December talk.
The James Webb?
Yeah, did I say that wrong? You said Hubble. Oh, I'm sorry. Yeah, James Webb.
Yeah, and maybe could you talk also about how images enable us to see those problems of physics? Because I've really tried to find more information about that online, and I can't find anyone really delving into that very much.
Well, it has to do with essentially with resolution, with what's called resolving power. So you can take the same image taken by the Hubble telescope and the James Webb telescope of something really far away, billions of light years away. And the Hubble image looks like blah. It's a splat. It's maybe a little dark spot or a brighter spot in the field of blackness. But if you take that same field of view and you take an image with the James Webb telescope, you see, oh, this is a splat, and it's got another splat near it, and they're this color red, which means they have these kinds of elements that are being excited within those bits of matter. And then if you look really carefully, you'll see a little bit of an Einstein ring distortion, so they're magnifying the light of things. Just because the resolution is improved and it's got these incredibly sensitive spectrographs that can pick apart what are the kinds of matter emitting the light frequencies we see, it can get a lot more data about things that look really tiny to us because they're so far away, which means they're very ancient. And so the James Webb telescope is an epochal advance in astronomy. Right.
Thanks so much, and thanks for being part of Science Sunday, everyone. Appreciate you.